So here let's talk a little bit about Bronsted Lowry acids and bases. Acids are proton donors. So proton is H+. If you remember the structure of a hydrogen atom, it just has a proton in the nucleus and there's an electron. So if you have H+, the electron's gone, all you've got left is a proton. So when we say proton, we mean H+. Bases are proton acceptors. So quick definition. This in parentheses is just something I would mention to you. You often see water as a product when you have an acid reacting with a base. It's not always. We have an example today we're going to look at where we don't produce water, but often you do see it. In Bronsted Lowry, with Bronsted Lowry acids and bases, conjugate acid-base pairs differ by a proton. And by the way, this is not real. This part isn't really part of Bronsted Lowry. They don't define it as that. It's just this: proton donors, proton acceptors. So let's look at nitrous acid and barium hydroxide. We're going to look for a net ionic equation, and we're going to look to identify some conjugate acid-base pairs. So nitrous acid. I ate ick to spite us. So nitrous relates to nitrite. Nitrite is NO2. And nitrite is -1, so there's one proton there, and that's aqueous. That's a weak acid. And barium hydroxide, Ba is group 2, so it's 2+, BaOH2, aqueous. And that's going to give us some products. We see the acids, they usually have this proton, usually it's written out in front, sometimes it's at the end of the molecule, but we've got this proton here. That's by itself to signify that this thing is an acidic proton. It can react, it can be donated. Hydroxides, well, they're nice, they can take a proton and become water. So when you're looking at acid-base chemistry, start to look for hydroxides. So what's going to happen here is these protons are going to combine with the hydroxide and give us water. And barium nitrite. Okay, so now we could do a net ionic equation. That's a BaNO2 aqueous, in case I ran out of room. So I'm going to do a net ionic equation. Net ionic equation, we split any strong acids or strong bases. Nitrous acid is a weak acid, so we keep it. Barium hydroxide strong. So on the reactant side we get that. Oh, I didn't balance it. So we have 2 hydroxide units here. So we need to have 2 protons. We're going to get 2 water molecules. All right, good. Did that change anything? Yeah, that's the same. So we have 2 water molecules and 1 barium ion and 2 nitrite ions. So we can get rid of any spectator ions, which looks to be just barium. And if we notice that all of our coefficients are 2, since the coefficients are all 2, we're going to reduce everything to 1 for a net ionic equation of okay, we've got nitrous acid, hydroxide, water, and nitrite. So okay, we can relate these. Conjugate acid-base pairs differ by a proton. So the acid on the reactant side, we're looking at the net ionic equation for the conjugate acid-base pairs. The acid is HNO2. And it is going to have a conjugate base of NO2 minus. All right, and the other pair, we have hydroxide, which is acting as a base. It's accepting a proton. Put that here. And water is its conjugate acid. So notice they differ by a proton, they differ by a proton. This donated a proton, hydroxide accepted a proton. All right, next one, potassium hydroxide and hydrofluoric acid. Potassium hydroxide, KOH. And we see a hydroxide. Hydroxide is going to take a proton. We see the two H's and an O. There's your water. Okay, and then we predicted products first. You could probably just make a net ionic equation first and get it that way too. Let's make a ionic equation. This is a strong base, so it completely dissociates. Okay, so we have 4 ions on the reactant side, 2 ions on the product side, and water on the product side. It's balanced. Let's get rid of any spectator ions. So we're not going to need the potassium. And we're not going to need the... What have I done? Oh man. I'm not restarting this. This is just dumb. Okay, so KOH. Hopefully the mistake that I just made will mean that you won't have to make this mistake on a test. HF is not a strong acid. All right, HF that's a special one that's in the special halogen kind of, or halide. This is not a strong acid, so we don't dissociate it. We keep it as HF. And this is going to donate a proton to the hydroxide. Keep that. And get rid of spectator ions. The only one, because there's only one thing that's strong here, the only one is potassium. So now our net ionic equation has hydroxide plus hydrofluoric acid yields water plus fluoride. Well, be careful with hydrofluoric acid. In real life too, if you ever get the chance. So let's look at this. We say, okay, hydroxide is our base. The conjugate acid that is water. Right? And then our acid is HF, and the conjugate acid is F minus. I'm going to stop this there and then continue with this.